students, welcome back to Rasayan. In this video, I am going to explain another application of resonance or mesomeric effect, that is stability of carbon ion. 3 carbon ions are given. You have to find out stability order. Now see here, double bond, single bond, negative charge. All are in conjugation. So here resonance is possible. So we can write here resonance. Here this carbon is sp2 hybridized and this carbon is sp3 hybridized. You know sp2 hybridized carbon is more electronegative than sp3. sp2 hybridized carbon is more electronegative than sp3. So here, if this carbon is more electronegative than this carbon, so negative charge on electronegative carbon is more stable than this carbon. This is because this is more electronegative. So here resonance is not possible. Here also there is no resonance. So due to resonance, this third carbon ion is more stable. Then since it is sp2, next stability is for this carbon ion and it is least stable. Because here this is sp3 carbon and here plus I effect of CH3 group is there, which will increase the negative charge density on this carbon. So it will destabilize this species. Here 3 carbon ions are given. You have to find out stability order. Now see, adjacent to this carbon ion, nitro group is there. Nitro group is having minus M effect and minus I effect. Both are electron withdrawing effect. So if you consider minus M effect, that carbon ion will get stability by resonance. Or if it is electron withdrawing minus I effect, then electron density of this bond will be attracted towards NO2. So negative charge density will be decreased. Okay, so the carbon ion is getting stability. But here see, this nitro group and this carbon having negative charge, they are not in conjugation. So here no resonance. No resonance. Only you have to consider minus I effect of nitro group. Here adjacent position of carbon ion, there is nitro group, so minus M effect is possible, minus I effect is possible. At the same time CH3 is having plus I effect. Here minus M, minus I. So this is due to plus I effect of CH3 group. This is less stable than this species because here only minus M minus I effect of nitro group is stabilize the carbon ion. So most stable is this carbon ion. Next is this one. And here there is no resonance at all. So this is last one. This is stability order. Now note down this stability order of carbon ions. Now see, this is benzylic carbon ion. 5 resonating structures are possible. That's why it is stable. So it is stabilized by resonance. Here 2 benzene rings are there. So obviously it is more stable than this one. Here 3 benzene rings are there. So it is most stable one. Here it is having benzylic carbon ion is having 5 resonating structures and allylic carbon ion is having 2 resonating structures. So this is more stable than this one. Now what is about this and this carbon ion? Here see, CH triple bond C minus. This carbon is sp hybridized. And here CH2 double bond CH minus. This carbon is sp2 hybridized, and methyl carbon ion hybridization of carbon is sp3. So percentage S character is increasing here. So when percentage S character is increased, electronegativity of the atom is also increased. So this carbon is most electronegative. Then this one, then this one. So negative charge is there on most electronegative atom than this one. So this is more stable than this one, and this is more stable than this one. This is 1 degree carbanion, this one is 2 degree carbanion, and this is tertiary, means 3 degree carbanion. So you see the stability order. For carbocation, you have seen tertiary carbocation is more stable than secondary carbocation, and secondary carbocation is more stable than primary carbocation. But here if you see the structure, CH3 group is having plus I effect. It is increasing negative charge density on this carbon due to plus I effect. This is 1 degree or primary. What is about secondary? 2 methyl groups are there. So here negative charge density is increased by 2 methyl groups. This is secondary. In tertiary, negative charge density is increased more because there is 3 methyl groups. So plus I effect of 3 methyl groups increasing here negative charge density more. Obviously this is more stable, then this one. So this is the order. Now next, compare the stability of these 4 carbon ions. Here this carbon ion is stabilized by resonance. Here at para position, nitro group is there. Nitro is having minus I effect and minus M effect. So it is nitro is having electron withdrawing effect. It will withdraw electron density. So negative charge density will be decreased and the species is stabilized. CH3 is having hyperconjugative effect and plus I effect. Plus I effect means it will donate electron density in this side. So negative charge density will increase by plus I effect and also by hyperconjugative effect. So it will be destabilized. What is about Cl? Cl is having plus M effect and minus I effect. But here for halogens, minus I effect is dominating, plus M don't need to consider. So due to minus I effect, it will abstract electron density and the carbanion will be stabilized. So which one is more stabilized? This carbanion is more stabilized due to minus M minus I. Both are electron withdrawing effect. So most stabilized carbanion is number 2. After that, which one? This one, because it will abstract electron density. Cl will abstract electron density due to minus I effect. So next is this one. Then it is not stabilized because hyperconjugative and plus I effect makes this carbanion unstable. So next stability is this one, number 1, and this is unstable. So 2, 4, 1, 3. It is decreasing in this direction. And always remember, resonance effect is most powerful effect, then hyperconjugative effect, and then inductive effect. Just make a note. Now next, compare the stability of these 3 carbon ions. Now see here, this carbon, negatively charged carbon is attached with another carbon. This is primary carbon ion. This carbon ion is attached with 2 carbons. So this is secondary carbon ion. And this carbon ion is attached with 3 carbon atoms. So it is tertiary carbanion. Now if you want to compare the stability of those species, what you have to do? See, here double bond, single bond, negative charge. Double bond, single bond, negative charge. Here double bond, single bond, negative charge are in conjugation. So everywhere resonance is possible. For example, take this one. So this is the next resonating structure. Similarly, here and here you can draw resonating structure. For all those structure, resonance is there. And all are having two resonating structure. So how will you compare the stability? We know primary carbanion is more stable than secondary. Secondary is more stable than tertiary. And here you can see this methyl group is having plus I effect. It will release electron density in this direction. So this species will become less stable. So this is least stable. Now between 1 and 2, which one is most stable? This is primary. So primary is more stable than secondary. So primary, then secondary, and this is tertiary, and here methyl group is there. It will release electron density due to plus I effect. So it is most unstable. Now see, third application of resonance or mesomeric effect is stability of free radicals. Stability of carbon free radicals can be explained by resonance or mesomeric effect. Now some examples we will see. Now find out the stability order between triphenyl methyl free radical, diphenyl methyl free radical, benzyl free radical and allyl free radical. For benzyl free radical, these resonating structures are possible. This is stabilized by these 5 resonating structures. Now see, what is about diphenyl methyl free radical? Here 2 benzene rings are there, so more number of resonating structures are there. For triphenyl methyl free radical, more number of resonating structures are there than this one. So obviously this is the most stable one, then this, then this. And here 5 resonating structures are there, and as for carbocation, here 2 resonating structures are there, so stability is in this order, it is decreasing. For allylic free radical, similarly what we did for carbocation, we have to do only here homolysis will take place. Dot CH double bond CH2. So here 2 resonating structures are possible. Here 5. So obviously this is more resonance stabilized than this one. Next one. Find out the stability order of these 4 free radicals. Here double bond, single bond, double bond, single bond, free radical. So this free radical will be stabilized by resonance. Here double bond, single bond, then free radicals. It is also, this free radical is also stabilized by resonance. Here this is secondary free radical. Here no resonance is possible. Okay. What is about this? This is C6H5 dot. Here this free radical is not stabilized by conjugation. But here hyperconjugation is there. So what will be the stability order? Here hyperconjugation. Here resonance, here more resonance, and this is not stabilized because free radical is not in conjugation. This is unstable species, and for one such type of hyperconjugation is possible because with respect to this free radical, here 2 alpha hydrogens are there, in this side also 2 alpha hydrogens are there. So for these 2 hydrogens, 2 hyperconjugative structure, for these 2 hydrogens similarly 2 hyperconjugative structures are possible. So you know preference of resonance is more than hyperconjugation. Obviously 4 is the most stable one, then 2, then 1, and this is unstable. Now see, between these two free radicals, this is allyl free radical, this is vinyl free radical. Which one is stable? This is stabilized by resonance. Double bond, single bond, free radical all are in conjugation. So two resonating structures are possible here, but this vinylic free radical is not stabilized because this free radical is not in conjugation. So obviously this is more stable than this species. So this video is till this. Thank you for watching.